Welcome to Data Science 1, Probability, linking probability to inference, likelihood ratio. Okay, some things we're going to need to remember. We're going to need to remember what a sample space is, random variables, probability distributions, independent identically distributed, and binomial distribution. So what I'm going to try to do again is show you some examples of how to come up with the ideas in inference without actually formally doing that, because the next section has a lot about developing inference with type 1 errors, type 2 errors, and just the general sort of basic theory of inference. And what I'm trying to show you here is how you can link probability to these inferential ideas and put together a various tests. Now, in this case, we're going to be looking at the likelihood ratio, which we kind of talked about before, but before I said we were interested in this sort of ratio, but we wanted to maximize it. Here, we're not going to be interested in maximizing it so much as just coming up with some sort of test. So here's our example. Otieno is a cattle farmer who has 42 head of cattle. For the help of the community, inspectors come around and assess the head of the cattle every now and then. Since there are a limited number of inspectors, they take a sample of his cattle each time. According to regulations, they're supposed to take a sample of 20% of the cattle at each time. He takes a random sample of their frequent visits and records how many cattle they actually inspect. Okay, so his question is, does the data show that on average the proportion of, or the appropriate proportion of cattle are sampled? So here's the data he sees. The first time they come, they sample 4 cattle. The second time they come, they use 10. The third time they come, it's 12. The fourth time they come, it's 6. And the fifth time they come, it's 7. So each sample here, this is a binomial experiment, right? There's a limited number of cattle, and we're interested in the probability or the proportion that get sampled. So N is 42, and P is the thing we're interested in. All right, so we're trying to see which is more likely. Is more likely that P is 0.2, which is what the appropriate level is supposed to be, or could P be a lower value, say like 0.15? So they're below the threshold that they need to be. So here's our data. What we can do is we can kind of build this out. I'm not going to show all the details, but I'm going to show enough details. So here, what's the probability of the data given a value of P? Well, it's the probability that x1 equals 4, x2 equals 10, x3 equals 12, and so on, because this is the data we see. Okay, we actually see this data, and once we've seen it, it's fixed. It's not random anymore. So that's a probability that x1 would have measured 4, x2 measured 10, and so on down the line. Now, instead of putting all the binomial parentheses in and everything, I just put in here K1, K2, K3, K4, and K5 for, like, here would be 42, choose 4, and then I would have here, let's see here, 42, choose 10, here 42, choose 12, because in the end of this thing, they're going to end up canceling out. So I'm just kind of putting a number in there as a placeholder right now. And K6 is all of these multiplied together and pulled out front. And then here you can see P to the 39 is the sum of all the exponents that are associated directly with P. And the 171 is the sum of all the exponents associated with 1 minus P. So this is we've boiled it down to this little formula right here. Okay, and we can use the same formula for both situations, because all we have to do is just change P and see which one is more likely. Well, in order to see which one's more likely, let's form a ratio instead of looking at these numbers, because these numbers are ridiculously small. I mean, you have to use scientific notation. It's stuff like 10 to the minus 42. Just really tiny numbers. But if we do a ratio, then it kind of wipes all of that out and makes it come up with something we can actually interpret. Okay, so here, what's the probability of the data when given P1 is the true value, and what's the probability of the data given P2 is the true value? Okay, well, right here we have our P1 and P2, right? P is going to be 0.2, and P2 will be equal to 0.15. So I can just plug this into my ratio here. So here's my ratio. I plug in my formula here, and notice K6 is going to cancel. It's going to cancel itself out because it's the same in both formulas. So that doesn't really matter. So here we plug in 0.2 in the numerator, and we plug in 0.15 0.15 in the denominator, and we calculate everything, and then we come up with this number, 2.346. Okay, so this says that the data is 2.346 times more likely using P1 equals 0.2 than using P2 equal to 0.15. Okay, so it says the data is more likely to have come from the value P1. Okay, this is the population parameter of 0.2. Okay, which is not sort of what you would have expected from the data. If you just looked at it directly, you say, well, there's a whole lot of times they didn't get more than 20%. So here we're just looking at the data directly and using this approach to see what happens. Now, question is 2.346 large enough to say that P should really equal 0.2? Well, that's a little bit harder of a question because this ends up to this idea of statistical significance. And statistical significance, while it has something to do with probability, it's not directly related to probability distributions. It's more of a more general idea, and we're going to talk about that later in the next section when we talk about inference on single sample parameters. So we're going to go through and talk about different types of errors. We're going to talk about how to actually come up with things like p-values and cutoff values that tell us what that number should be. But I'm just giving you a flavor for here's how we're going to put these things together later in these other sections so that you can see how things work. All right, so I think this is good enough for this section. And so what did we learn? Knowing the probability distribution of the random variable associated with the actual experiment is important. Just don't assume it's normal. That's what most people do, and that's the biggest mistake they can make because you really should think about your experiment and what the distribution is. We can calculate the probability of the data given values for the parameter, and we would call this a likelihood. We can form a likelihood ratio and allows us to make decisions about population parameters. These are parameters that belong to the population, not to the sample. So keep that in mind as we're going through this. All right, so we're going to stop here, and I'll let you jump into the next section, which is inference on single parameter distributions and single, I think, populations. All right, so I'll see you there.